Hello friends, my name is Satyendra and today in this video lecture I will explain you about the variational method. The variational method is also called the variational principle in quantum mechanics. Variational method is used for evaluating the energies of ground state and first few discrete energy states approximately. Variational method is used when stationary perturbation theory cannot be applied successfully. So in this part you have seen what is the use of variational method. Okay, so variational method is used to find the energies of ground state. Okay, it is widely used to find the energies of the ground state approximately. It can also be used to find first few discrete energy states also. Okay, variational method is often used when the stationary perturbation theory cannot be applied. In order to understand the basic working or the basic principle of variational method, we have to understand some concepts before that. Okay, let's see those concepts. Okay, so if psi 0, this is psi 1, psi 2 are the exact orthonormal set of eigenfunction of Hamiltonian edge of the system. This means that if these psi are eigenfunctions of the Hamiltonian edge, okay, and these psi sorry and these psi are orthonormal to each other, okay, then we can write the following equations. Okay, so this is the eigenvalue equation for the ground state. This is the ground state and this is the ground state energy. The ground state energy can easily be found by finding the expectation of H as it is written here. Okay, and this expectation in Bryant-Cat notation can also be written like this. This 0 indicates the ground state in both the sides. Okay, so this whole term can just be replaced by this 0. Okay, so this is the ground state. Similarly, the other first state, this is the eigenvalue for the other states. Okay, these two and so on. Okay, so if we take the expectation of the first state, then you get the first energy of the state psi 1. This is the energy of the state psi 1. Okay, so in general these equations in general can be written in this form, where n is equals to 0 1 2. Okay, so it can easily be seen that En can be greater than or equal to E0. For E n equals to 0, it will be equals to E0, but for other values of n, for example 1, it will be greater than E0. So in combined form it is written like this. So at this point it is important to note that These psi are the exact eigenfunction of the Hamiltonian H of the system. Now it is written here, E0 is the lowest ground state energy. Now let phi be the linear combination of psi 0, psi 1 and psi 2 and so on. Okay, so this linear combination is written in this following form. Here phi is the linear combination of phi psi 1, psi 0, psi 1, psi 2. In short, it can be written like this. Okay, so n runs from 0, 1, 2 up to dash dash dash. Okay, up to infinity it can go. Okay, so now you might be wondering how I can write this. So the answer is here. This is possible because psi 0, psi 1 forms the complete orthonormal basis set. So these psi's are orthonormal. That means if their subscripts are unequal, then it will give you 0, but if they are equal, they will give you 1. So the scalar product is orthonormal. So it is a fact in mathematics that if the basis sets are orthonormal, then you can expand any other functions in terms of these basis set. Okay, in order to understand this expansion, I will take a very simple and familiar example that you have already studied in your lower classes. Now we will take an example in 3D space. So in 3D space, 1 0 0 0 1 0 0 0 1 are the bases, and any vector can be written in linear combination of these. Let me explain you. So this is the vector, as you already know. So in short, it can be written like this. Okay, it is also the notation of the vector. Now this can be written in this form. If you add all these quantities, you will get this. Now what we can do, we can take out x from here, because if you multiply the x inside, you will again get this. You can write this term like this. You can take out z from here, it will come like this. Okay, let's call this much quantity as x1. Let's call that's chi. So that this, let's call it basis 2, that is x2, and let's call it x3. Okay, so you have three bases. Okay, now you can easily see that these bases are orthonormal. That means if the bases are unequal, if their bases, you take the unequal bases, that will definitely give you 0, and if the bases are equal, that will definitely give you 1. Okay, so this is the property that you can see. If your bases are orthonormal, then you can express any vectors in terms of your bases. Okay, so what we have seen before, okay, so this is how this expansion is made, because these size are orthonormal. Okay, so we are clear till this equation. let's proceed further. Now, the energy of the state psi, we already know that psi is the linear combination of, sorry, the phi is the linear combination of psi. So the energy of the state phi, the energy of the state phi, or the energy of the system, okay, is written in this form in quantum mechanics. Okay, so this is the energy of the state phi. Okay, you might be wondering how I can write this. So let's look at this point. You might be wondering I came how this equation came, so we know that the eigenvalue equation for the state phi is here. Okay, so the eigenvalue equation is here. E phi is the energy of the state phi. This H is the Hamiltonian operator of the system. Now, operating by this bra from left, you will arrive at this equation. You can see at this point we have operated. Now in this section, E phi will come out because it's the eigenvalue, and eigenvalues are constant, so it will come out, and then we will solve this equation for E phi. So E phi will become equals to this. Okay, so this is how the energy of the state phi is written. Okay, now according to the variational principle, the energy of the state phi is always greater than or equal to the ground state energy. So this is the basic statement of the variational principle. So this is the energy of the state phi, which is the linear combination of all the orthonormal states. E0 is the ground state energy of the system. This is the basic statement of the variational method. Okay, so that means, that is, the energy E phi will always be greater than or equals to E0. This is the basic statement of the variational principle or method in quantum mechanics. Now I will, in further section, I will show you, or I will prove you this equation number 3. Okay, that how this came. Now we have already seen this equation. This is the equation number 1 in our previous explanation, and we have also seen the energy of the state was this. Okay, this energy of the state is written in the bra and cat notation, and it can be written in the form of integration like this. Okay, and this scalar product is written like this. Okay, this all space means in the x direction you have to take from minus infinity to the plus infinity. In the y dimension you have to take from minus infinity to the plus infinity, and for z you have to take from minus infinity to the plus infinity. These will be the limits of the integration that will fill the all the space. Okay, so at this point, this d tau is the volume element in rectangular coordinate. If you talk about the rectangular coordinates, then d tau is equals to dx dy dz, and it has the notation d3 cube, sorry, dr cube. Okay, so in our further proceedings we will donate the all space by this tau. Okay, so I have replaced the all space by tau. In here also I will write tau in my further equations. So now I have plugged the value of this phi from this equation in this equation everywhere, so that becomes like this. So this equation becomes like this equation. You can see that, okay? Now this part was the constant, so came out of the integration, and this was also the constant, so came out of the integration. In our previous equation, summation came 2 times, but it is running over only one index, that is n. So that's why the 2 times summation is written only one time. Similarly here, we have written the summation only the once because it is running over the same index n. Now we have to simplify this equation because already explained that the size are orthonormal, so their scalar product is equals to Kronecker delta, and that is equals to 0 if they are unequal and equals to 1 if they are equal. So at this point this should be equals to 1 because they are same, so their scalar product should be equals to 1. Okay, now we have to worry about this thing. Okay, now we know that this equation, as already explained you, now if you operate on both the sides by this bra, then you will arrive at this equation. Now this En is the eigenvalue, this was the eigenvalue, so it will came out because it is constant. You may know that En is the eigenvalue and En is the result of the measurement of the energy, so En is constant. Okay, so it came out, but this is 1 as already seen because these are equal psi, so it is 1 and your En is equals to, so this quantity is equals to En, so I will plug the value of this. Okay, so now putting the value of this quantity from equation 5 and the value of this quantity, which in turns equals to this, equals to En from equation 6 in equation number 4, that is equation number 4 is here. This was equation number 4. We will put the value in this equation and we will get this equation. Now subtracting E0, this is the ground state energy from both these sides of the equation. Okay. So here I have subtracted, you can see that. Now I have further simplified it by taking the LCM. Okay, so it came like this. Now in this part, this is the common, so it came out, and then this and this got cancelled and we are left with this equation. Now I have already explained you that En may be greater than or equals to 0. Okay, so because n may be equals to 0, 1, 2, 3, so when n equals to 0, that will be equal, so E0 will be equals to E0 for 1, E1 will be greater than E0, so this is equation. So finally this means that En is greater than E0, that means their difference should be greater than 0. Okay, now I will plug the value of this quantity, so that this quantity has this value, so I will plug this value here and I got this. This means that the difference is positive or greater than 0, that means the E5 should be greater than E0 or equals to. So this was the basic statement of the variational method, which I have just proved to you. So this proves the variational method. The physical meaning of this is that the energy of any state of the system should be either equals to the ground state or it will be greater than the ground state. Now I will give you the basic working method of the variational method. So how the variational method is used to solve the questions is described in this section. This method is used to find the energies of ground state and first few discrete energy states of the bound system. So here I have to write energy states, okay, approximately. So it approximately finds the energy of the ground state. So the working method is here. First, you have to choose the trial wave function, say phi. You don't know exactly what is the function, so you have to take the trial wave function phi. And your phi should the phi depends on the variational parameters like c1, c2. So phi is the function of the variational parameters. These parameters are variational because these parameters may change, they may vary, okay. So your phi has to be chosen that it should depend on some variational parameter. So this is your trial wave function. You first have to choose the trial wave function. Now comes the part B. In the part B, you have to find the energy of this state. So the energy of this state phi is given by this in quantum mechanics, okay. Here H is the Hamiltonian operator of the system in consideration. On solving this, you will find E phi is the function of the parameter C1, C2. So on solving, you will find that E phi is the function of the variational parameter. Either this can directly give you the ground state, or further if not, then we have to find the minimum ground state energy. Okay. So in the third step, okay, which step? So in the step C, that is the third step, the parameters C1 and C2 are so chosen that E phi is minimum, and this is achieved by solving these minimum conditions. So these are the conditions where when the energy E phi, or these are the conditions when the energy of the state phi will be minimum. So solving these equations, this will give you those values of the variational parameter for which the energy E phi is minimum. So finally, on solving the these equations, you will find out C1, C2, okay. In this step, putting the value of C1, C2 in back in this equation, back in this energy relation, in the formula of this energy E phi, you will get the ground state energy, okay. So for better understanding of the variational principle or variational method, I will give you a very good example, okay. So keep watching. The video is going to be little longer, but you will enjoy it, don't worry. So in order to explain you the method better, I will take an example which was asked as a question, as an example which was asked in CSIR net June 2014 in physics stream. So the question was, the ground state energy of the attractive delta potential where V is greater than 0, calculated with the variational trial function, okay. So they are asking us to find the ground state energy, okay, where they have given us the attractive delta potential, and they have asked us to calculate this ground state energy with the help of trial wave function. This is the trial wave function, okay. This is defined here. The trial wave function is defined here for x in this region, okay. Here you may see that a is a constant, some constant, and this small a is the variational parameter, okay. So for this range of x, the function is defined, but for the other values of x, then this function is not defined. Okay, so it is important to note that this condition, this range can also be written like this. Okay, it can also be written like this. Now this potential was given. Okay, the trial wave function is also given. This is the trial wave function. Now in this trial wave function we are unaware of this a, so the first thing is to find out a, and in order to fix this a we will use the condition of normalization, which is this. Okay, so this is written in this integration form like this. This is the all space. Okay, and we will take the proper limits. Okay, now at this point I have substituted the value of this psi. Okay, so at this point I have taken these limits properly. Okay, so you can read it. These limits are used because psi are defined for this range of x only, as it was given in the question. Okay, now we can see that this is the real quantity, so conjugate will not have any effect in this, but we are unaware of this. It may be complex also, so let's write the complex conjugate over this. Okay, now these two things are constant, so this will come out, and we are now left with this much. Okay, now it cannot be integrated, this part cannot be integrated directly. We have to apply this identity from trigonometry. Okay, and we also know that this is equals to this much, so we wrote this and I applied the identity. Okay, so we got this equation. Further this came out because this is constant. Okay, so we then got this equation. Then I used the linear property of the integration, so it went to it got distributed. Okay, so we got this equation then, and then I integrated it. So I know that the integration of the sine is cos, sorry, integration of the cos is sine. Okay, so I used that identity, okay, to solve this. Okay, and then also I integrated this part, and I then got this part. Integration of just one is x, so I wrote that. Okay, now in this part I have, since this is constant, it's taken out. Okay, and the limits are put at this point, so you got this equation. Then I applied the limit in this point, so we got this equation, and this is simplified. Then it is further simplified, this part is further simplified because this a will get cancelled on both the side, and this minus will come outside, and that will become plus in the next equation. So we got this equation then. Now since the value of sine pi, you can see that the value of sine pi is 0, so that's why it's 0. Also so we simplified this thing. Also this will also be 0, so this came to 0 because sine pi is 0. Okay, so we got this equation then it is further simplified to this, and then this 2 and 2 got cancelled. Okay, I was left with this, and then I further got this equation. Okay, so the value of a is 1 over root a. Now with this value of a, the trial wave function, that is equation number 1, will become like this. So this will be the now trial wave function. This is the value of a which is substituted, and this is defined only for this value of x, or you can write it like this also. Now we have to find out the Hamiltonian of the system. We are still unaware of the Hamiltonian of the system. Okay, so we know that the Hamiltonian is the sum of the kinetic energy and the potential energy. Kinetic energy is just p square upon 2m, and this is the potential which was given to us, attractive delta potential from question. Now the energy of the state phi is here, as already explained you in the variational theory. Okay, but at this point we have already normalized our state, so this is just 1, so this will be 1. Now, so the energy value of energy will be this. I have written the value of this Hamiltonian at this point. Okay, so we got this equation. In the further step, I have then separated the operators and used the Bryant cat properly, and you can see this. Okay, now at this point I will plug the value of this momentum operator. Okay, so it is written here, the value of momentum operator is plugged at this point. Okay, now I further I have squared that, so the operator becomes 2 times. Okay, and that became like this and this. Okay, so this equation is now clear to you. Okay, now this was the constant, so it will come out and you will be left with this and this. Okay, now at this point I have to plug the value of this phi. Okay, but before that I will write this Bryant-Coit notation, expectation in Bryant-Coit notation in the integration form like this. Okay, so now I have plugged the value of, now at this point I have plugged the value of this and this here and here. Okay, so you can see that it's now became a complicated. Okay, but it's too easy. So here you can see that there is nothing complex, so the conjugate will not have any effect. Here also the conjugate will not have any effect because this whole is the real quantity. Okay, so the equation becomes like this. Now I have to operate this differentiation inside this. Okay, so I did that. Okay, so now I arrived at this equation. Okay, in this step I have differentiated that part and I got this, and I have then multiplied this and this together and I got this. Okay, now in order to solve this part, because this involves the Dirac delta function, it is not so easy, it won't be easy to solve this directly, this integral. So we will use the property of the delta function. The property of the delta function is written here. You should remember this property, it is very important property. Okay, so for a equals to 0, this should become like this. Okay, so we will use this equation. Now in this part, okay, so in this part again we have to differentiate this, and there the equation will become like this. Okay, and now I have done one substitution, is that this part is taken as gx. You can see this gx equals to, okay, so now we have this equation. Okay, now you can see we have already shown you the formula for the delta function, so this should be equals to g of 0. Okay, according to this identity. Okay, so we have this equation. Okay, now we have to integrate this part, and so I have used one formula to I have used the formula which I have already explained you. Okay, I wrote that formula. Okay, and this g0, g is the g of x was the cos square, so I have put the value, and the value of cos 0 is 1, so here it will be just 1. Okay, so finally further I have integrated this part, so the equation become like this. You can see it. Okay, you can go through this. and then further it is further integrated and you got this equation. Okay, you can go through this equation. Now you can see that how I have solved it further. Okay, so here some things will cancel down as okay. So you can see this equation. Okay, I will hold the screen for a while. Okay, so that equation is clear to you. Now this sine pi and sine pi is 0, as you can see from here that the value of sine pi is 0. At pi, sine pi will become 0. Okay, at this diagram. Okay, so this will just go to 0, this whole term will just go to 0. Okay, so you will be left with this equation, and now that equation can further be simplified like this. Okay, you just have to do some simple operations mathematically, and then you will arrive at this, and then you will arrive at this. Okay, so you can go through this. I am zooming the screen. Okay, so you arrived at this. Finally your energy of the state psi is this. Okay, so as already told that E phi is the function of the parameter A, we have to minimize E psi with respect to A. So the condition for the E psi to be minimum is this. Okay, so this is so when E psi is 0, so sorry, E psi is minimum. So when E psi is minimum, its derivative with respect to x should go to 0. So I am differentiating it with respect to A. I have differentiated here, and then I simplified at this point. You can see it. Okay, now on further simplification it become like this, and it can be solved, and then it can be further solved like this, and then like this, and then A will become equals to this. So at this value of A, E phi will be minimum. Okay, so putting the value of A in this equation, okay, in the equation of energy, okay, we get the ground state energy. Okay, so I've in this equation of, so E0 denotes the ground state energy. Okay, so the value of ground state energy is given when we will put A equals to this much. Okay, so I have put that value of A, and then further simplified it. Further I again simplified it. Okay, and then I again simplified it. You can see that. Okay, you can see that. Then I have taken the LCM, and then this is the answer. This is E0. So this is the answer of your question. This is how the variational method works. Okay, thanks for watching this video. If you like my video, please share with your friends, like and subscribe this channel, and thanks for supporting this channel. Okay, thank you very much.